Hey folks, I forgot to add this little extra example at the end of last time's notes. So let's look at what happens. We need to be a little bit careful when we talk about the end behavior based on the end behavior model. So once you clean this up, we get negative 2x. All right, now when I sketch negative 2x, that end behavior model does a nice job. One goes, as I go towards the positive, my graph goes negative. As my graph goes towards the negative, my graph goes positive. But we've got to be a little bit careful if our exponents reduce and it's not just a single x. So what I mean by that, let's take a look at f of x equals 3x to the fifth plus blah, blah, blah. I don't even care what the rest of it is. Over 2x to the third plus blah, blah, blah. All right, now when I clean this up, my end behavior model would end up being 3x to the fifth over 2x to the third, which then would clean up again into being 3x squared over 2. So you've got to be, what I mean by being careful here, if I'm going to sketch this, you have to think about what an x squared graph looks like. An x squared graph is going to look like this. So my end behavior model, where they both would be the limits both approach infinity. So what I'm saying there is just be careful that it's not always one goes up, one goes down. It's going to depend on what you're left with. If you're left with an x squared graph, then they're both going to go up. Or maybe this is a negative. If I throw a negative in here, then all of a sudden this graph is going to be a parabola that opens downward, and then both limits would approach a negative infinity. So just something to be aware of, something to be careful of. All right, so moving on to the next part. So sometimes they can be a little sneaky about how they give us a function. So the degrees of the numerator and denominator are not explicit. This often occurs when under a radical. So in other words, it's sometimes a little tough to see how this graph behaves. But I'm going to still use my plugging in negative infinity and positive infinity model and see where that gets us. So first of all, what's the only thing I care about? I care about 4x, and I care about 9x squared underneath the square root. Now I'm going to include that. I'm not going to clean it up first. I'm going to plug in my infinities first and then clean it up after. So if I try to, hold on a sec. So if I want to figure this out, okay, let's start by plugging in our infinities. So it would be 4. So let's try to, what would be a nice way to organize this? Yeah, I'll just write it, I guess. 4 times infinity over 9 times infinity squared, getting square rooted. Now I start to clean this up. I would have 4 times infinity over, and now I'm going to square this first, so keeping track, if this is negative, you're going to have to take care of that first. Now it might seem like, well, it's not going to matter because no, it does, because if I cancel the roots right now, in this case, it's not going to matter. I'll move on to the next one when it does. Square root of 9 is 3. Square root of infinity squared is infinity. Infinity over infinity is a tie, so we're left with 3 over 4. What's more interesting is the negative case. So that's going to be 4 times negative infinity over 9 times negative infinity squared. How does this behave? This is what I was talking about in the last video. You've got to be a little bit careful. This plugging in infinity is nice, but you got to be a little bit careful about how you clean things up. So what I would do, 4 times negative infinity would be negative 4 times infinity over, and then now here I would attach the squared first before I can square root. So what happens is this ends up becoming a positive. So I would have the square root of 9 times infinity squared, which then would clean up to be negative 4 infinities over square root of 9 is 3. Square root of infinity squared is infinity. What's going to happen to those They're going to cancel, and then this is going to level off at negative 4/3. That's what I mean. You got to be careful, because if you just cancel right off the bat, square root of 9, square root of 3, and you just have 4x over 3x, that's not going to work. It's not going to be the true end behavior. Let me just prove it to you. Well, I'll write it up first. So I would say the limit. Determine the end behaviors of the following functions. Write equations of any end behavior asymptote. So that's the HAs and the SAs. So the limit of f of x as x approaches infinity was 4/3. The limit of f of x as x approaches negative infinity is negative 4/3. Let me just prove it to you that that's true. So I can clear out my old stuff. This is 4x subtract 2 over the square root of 9x squared plus 8x plus 1. Now, if this is right, I should have two different HAs. Actually, I'm going to go real small here to the 5. Let's go to like 3. No, too small. Here's one HA. Here's one HA. There's my 1. As I go towards the negative infinities, my HA levels off at y equals negative 4/3. And then my other, as I head off towards positive infinity, my y values level off at positive 4/3. So they both, just to prove to you that you can't just, if I would have cleaned it up first and got 4x over 3x, those x's would have canceled, and I would have said that the end behavior is always 4/3. That's not true. So cleaning up with the by plugging in negative infinity, you got to be a little bit careful. So I would say my end behavior asymptote, I'm just going to say that it's an HA. HA of y equals plus or minus 4/3. Both of those ended up being horizontal asymptotes. Let's have you try the next one. Pause it, give it a whirl. All right, let's see how you did. So in the numerator, I only care about negative 2x cubed. In the denominator, I care about the square root of 11x to the 6th. Now I'm going to plug in my different infinities. So we would have, yeah, the bell's going to ring. I'm going to pause here. All right, let's see how I do picking up after where we left off. So, okay, so here we are. So I've got this is my end behavior model. Now I'm going to start to plug in some infinities. So let's see, that would be negative 2 times infinity cubed over, and then this is what I was talking about. You got to be careful. We can't clean this up first. We have to plug in the infinity and then clean it up after. In this case, it won't really matter, but in the next one it will. So let's see, an infinity cubed, so I would end up with negative 2 infinity cubed over. So I would take the infinity to the 6th first, which is still going to leave it as positive. That's no problem. And then I'm going to square root both of these. So I would get square root 11 times infinity to the 3rd. So just like the square root of x squared is just x, those would cancel. The square root of x to the 6th, you'd get half as many of them. So now it's a tie. So I've got infinity cubed over infinity cubed, which leaves me with just the coefficients. Now let's try this again with the negatives, and that's the one I really want to talk about. So we've got negative 2, negative infinity cubed, over 11 times negative infinity to the 6th, getting square rooted. All right, so negative 2, negative infinity cubed is going to be negative, but the negative and the negative is going to make a positive. So I'm going to end up with positive 2 infinity cubed over. All right, so you have to apply the negative to the 6th first. So that's going to be negative to the 6th is going to end up making this thing overall positive infinity to the 6th. But then I'm going to square root that, so I get root 11 times infinity to the third. Okay, so it's a tie. Infinity to the third and infinity to the third leaves me with 2 over root 11. And now I can write up my end behavior. I like to write up my end behavior with properly cleaned up. This is a free response, so you could stop here. You don't have to clean up those roots on the bottom. I'm going to because I like to. It's always kind of risky to do that, though, on the AP test, because if you screw it up, you lose points for something really silly. But anyway, you remember how you would clean this up? You'd times by root 11 over root 11. So negative 2 root 11 over 11. And then my limit of f of x as x approaches negative infinity. So when we plugged in negative infinity, we got out positive. And then I'm going to rationalize. And like I said, if you don't want to do that, I'm okay with that. Now, if that was a multiple choice, you wouldn't have an option. You'd have to clean it up. Do we have any HAs? Well, do we have any limits? If we have a limit, you have HAs. So my HAs are those two values. So I'm just going to say plus or minus 2 root 11 over 11. Let's have you try the next one. Next one's pretty easy. Pause it, give it a whirl. So my end behavior model would be negative 5x squared over the square root of 11x to the 6th. So now I'm going to plug in again. Let's see, which way do I want to go this time? So let's see, it would be negative 5 times infinity squared over 11 times infinity to the 6th. So that's still going to be negative 5 infinity squared over. And you might say, why don't we just make infinity squared infinity? Well, we have to compare the infinities. So that's why it gets a little bit tricky, that you want to leave the infinity in there. So I'd get root 11, and then I'd have infinity to the third. Ooh, that's interesting. More infinities on the top or on the bottom? On the bottom. So that the bottom wins out. That means it's going to be overall heading towards 0. So negative 5, I probably don't even need to waste my time doing this, but let's do it anyway. So this negative gets squared, so I'll have a negative 5. So that negative got squared out. Same thing here, this negative gets raised to the 6th power, so that's gone, and then I can root it, root 11. And then I have, again, more infinities on the bottom, so that's going to level off at 0, which means we can now find the limit of f of x as x approaches infinity would be 0. The limit of f of x as x approaches negative infinity is 0. And if you have limits at infinity, then you at a number, then you automatically have some HAs or SAs, I suppose. Well, no. If it's infinity, that's when it would be an SA. Y equals 0. Okay, now the next part, I don't know if it's kind of interesting, so I'm going to go over it. He's got some bonus problems here. Limits at infinity bonus problem. So he kind of broke down how functions, listing the functions in order of how fast they grow. So list of functions by how fast they grow for large x in increasing order. This is not something I've noticed as one of the big topics for the AP test, but I mean, it might show up as a multiple choice question. So these are the slowest growth at this end, slowest growth to fastest growth. So for instance, I mean, look at the first one, the constant function. If you just have a constant graph, y equals k, that's just going to straight up be this. How far is this growing? This is no growth. That is showing 0 growth. Y equals log of x. You should be able to sketch this. Pause it and try to sketch it. Hopefully you drew something like that. There's the graph of log. Y equals x to the n. These are all of your polynomials. Polynomials would be something like x cubed, maybe. I'm going to sketch an x cubed here. What's next? B to the x. That's an exponential growth. You should be able to sketch this without my help. Exponential growth. Should look like that. And then the next one's y equals x factorial and y equals x to the x. I have no idea what they look like, and I don't expect you to either. Okay, so what he's doing on the next page is he's kind of, and this is not something I would memorize. I don't. It's kind of interesting, and you might be valuable, but it's not one of the big ideas. So what he does now is he takes two of these functions and he compares them. So basically, you're trying to figure out, is the top growing faster or is the bottom growing faster? So an x to the cube versus an exponential. So this is a polynomial versus an exponential. A polynomial is a little bit slower than an exponential. So I would say this is a little bit slower. This is growing a little bit faster. So if the denominator grows faster, where does your limit end up? Your limit ends up at 0. So for instance, on the next one, what is this? This is no growth. No growth divided by, well, this is some sort of growth, right? This is 5x, which is growing. So this is some growth. I don't know. It grows. And I don't care how it grows as long as it grows faster than the top. So this also would end up limiting out at 0. So do the rest of these. Maybe you pause and you look back and forth. Like I said, I don't care if you memorize. So pause, try to do this next one. Okay, I'm comparing natural log with the root. Natural log goes in the same world as exponential. Nope, sorry. Log is right here, and then a root falls in the same category as a polynomial. So this is slow, but this is slower. So this is slower. That means the bottom is growing slowly, but it's slower than slower. So it would level off at 0. Like I said, I don't love these examples, but I'm going to just put them in the video just to make sure I have them. Okay, what do I have here? 100 to the, that's an exponential, but I'm comparing it to x over x. That's the fastest. So while this is fast, this is the fastest. So the bottom is getting faster. We get 0 again. All right, x factorial over, so this is faster. This one is faster. That's really fast, but this one's the fastest again. So the fastest is going to grow bigger on the bottom faster. So that's going to end up at 0. And let's see, oh, they just reciprocaled it. So this one is the fastest divided by faster. Faster gets beat by fastest. So this grows the fastest on the top, which means the top gets bigger, which means it levels off at infinity. So like I said, if you don't remember these, I don't remember these, the order of these either. It might be worth it. It might be kind of fun, but I don't know how important it is. These last two, I would say these are ones that you should be able to do. So let's try to calculate this thing. So I'm trying to find the limit as x approaches infinity. Nothing cancels as much as you want. These decancel. It's just not true. So we can't cancel them out. So what I'm going to do is I'm going to start to plug in infinities. 8 minus 3 to the infinity over 4 plus 3 to the infinity would equal 8 minus, okay, 3 to the infinity. 3 to some massive number would be infinity. 4 plus 3 to some massive number would be infinity. Or another way you could think about this is doing a quick little sketch. What does the sketch of 3 to the x look like? Any exponential growth looks like this. So as x goes towards the infinities, my graph goes up towards positive infinity. So what's 8 take away infinity? Negative infinity. What is 4 plus infinity? Infinity, and we'd end up with negative 1. Same idea here. Let's have you try this one on your own. Okay, so I'm going to plug in the negative infinities. Two ways to think about this. You can think about this as looking at the graph and saying what's happening as we go towards negative infinity. Or you can think about this as a negative exponent, which means flip around. So 8 over 1 over 3 to the infinity over 4 plus 1 over 3 to the infinity. 8 minus 1 over, okay, what's 3 to the infinity? 3 to infinity is infinity over 4 plus 1 over 3 to, that's also infinity. But what's the reciprocal of infinity? If you take one pizza and you divide it by everybody on Earth, you're not getting much pizza. So it ends up being 0. 8 minus 0 over 4 minus 0 ends up being 2. So if you go back up here, we could have done that right away because as x goes towards negative infinity, my y values get closer and closer to 0. So you could have cut right from here right down to there. And just to prove that I'm not crazy, 8 minus 3 to the x over 4 plus 3 to the x. Here's my picture. As x heads towards positive infinity, my y values head towards 1, negative 1. As x heads towards negative infinity, my y values approach 2. All right, folks, so that's it. Those are the notes for 1.3. Good luck.